absolute value of the secant, what it boils down to. See that? Now, because our domain, let's see here, our domain is negative pi over 2 to pi over 2. See, we do need the absolute value bars around the secant because secant can take negative values. We want the magnitude of v to be a positive number. Magnitude has to be positive. But secant could be negative, but at least on this domain, the secant is always positive, so we can do away with the absolute values around the secant. See this little thing? See, on these values of t, the secant function is positive. So we don't need the absolute values around. All right, so we get that the magnitude of v is the value of the secant of t. And that's what we had to divide that into this vector v to get the capital T. So we take this vector and divide by secant t. But secant t is reciprocal of cosine t. So dividing by secant t is the same as multiplying by cosine t. So I'm multiplying this vector by cosine t. Scalar cosine t. So I multiply this component by cosine t, but tangent t is sine over cosine, so I get the sine. And when I multiply 1 by cosine t, I get cosine. So the unit tangent vector turns out to be this simple construction. After all of this calculation, there was no shortcut to this now. We had to do every single thing we did here to get that the unit tangent vector for this function is this unit, this vector here. Note that a check on it is that it's a unit vector. For all values of t, this is a unit vector because its magnitude is 1. Sine squared plus cosine squared is 1. So if it didn't turn out to be unit, it wouldn't be a tangent vector, so it wouldn't be a unit tangent vector, so it couldn't be right. So if we haven't made any mistake, all this calculation has gotten this to be the capital T. That's the first thing they asked us to do. Compute capital T. Now I'm going to skip the end and come back to it. Let's go ahead and compute kappa now. Remember, according to our formula, kappa is the magnitude of t prime divided by magnitude of t. Well, we already got this magnitude of v right here. It's secant t. Now we need the magnitude of t prime. T prime here is the derivatives of this. So I take the derivative of capital T, and I get, again, I'm using C and S. Derivative of sine is cosine, derivative of cosine is negative sine. So I get that vector. But I want its magnitude. But because it's a unit vector also, its magnitude is 1, which is nice. So therefore, we get that the magnitude of t prime is just 1, and the magnitude of v, as you said, was, so we get 1 over secant t, which is just cosine t. So kappa on this domain takes the value cosine t for each t. That is the curvature. Now the curvature of a curve as a number, it's a positive number that represents how fast the curve is bending. The smaller kappa is, then the less bend there's happening. A straight line has a kappa of 0. There's no bend whatsoever. A circle, a big circle, has not a very large kappa because it's not having a bend. The kappa for the Earth, the equator of the Earth, is probably very, very tiny. But the kappa for that circle would be much larger. And the smaller the circle gets, the kappa is gianter and gianter. They say that some of this stuff about higher dimensions could be that the kappa, the curvature of particles, energy particles, could be that the particles are so, or even if they're flowing, if they're bending so much that their kappa is enormous, that they're almost like a point, although they're really just little circles. You see, they're going in little circles, but they could be so small a circle that they're almost like a point because the kappa is so large. But there's a lot of that. They talk about the curvatures anyway. the calculation is right here. The smaller the circle, or the faster the curve going like this, its curvature is not very much, but suddenly it makes a big turn, and its curvature suddenly increases quite a bit to make a big turn. So the tighter you turn, the more the kappa is. And so that's what we're calculating here. It turns out for this curve, its kappa varies as cosine t. Some maybe see when t is 1, when t is 0, the curvature is 1. But then as t approaches pi over 2, the curvature is approaching 0. So it's starting to flatten out as we get near this pi over 2, because the cosine of pi over 2 is 0. So the kappa. Now finally, we get to this thing called the unit normal. Let's define it. This section is dealing with the principal unit tangent and the principal unit normal. We're using capital N for principal unit normal. And on page 922, it is defined as the rate of change of the unit tangent with respect to arc length divided by the curvature. Or as they say, 1 over the curvature times the rate of change. But again, you don't want to compute it using that formula. It's better computed using the formula down below. So we'll use this formula. So these are the formulas you should be learning and writing on your formula sheet or preparing to use. So that the n is, to calculate it, it will be t prime. Prime means with respect to little t. And we're going to divide that by magnitude t prime. See, remember we had the unit tangent was v divided by magnitude of v. In other words, which is the same as r prime divided by magnitude of r prime. The original curve, r, its derivative is v, and you divide by its own magnitude, you get a unit tangent. Now you just do the same thing with this unit tangent. You do t prime and divide by its magnitude, see? So you get the unit normal. This is unit because we're taking a vector dividing by its magnitude. The unit normal now should be like acceleration. It should point normal to the curve. The tangent points along the curve, and the normal points, the normal should point more or less in the direction of the bend of the curve, if there is a bend. So the tangent points along the curve, and then the normal will point into the bend of the curve. And that's it. That's its formula. So they wanted us to compute that. In other words, learning to do computations based on these definitions. So for here, we got our t, we got our kappa. Now we have to differentiate t. There's t prime. But t prime, so n will be this thing divided by its own magnitude. But we just determined its magnitude was 1 when we did the kappa. So this one was an easy problem in the sense that we've already determined that t prime's magnitude was 1, and so we're just getting that n is t prime. In other words, t prime is unit, so to unitize it, it stays itself. So the normal is t prime for this particular case. In general, of course,